We directly move on with the next presentation before the lunch break, the last presentation before the lunch break. It's about defining standards in quantum computing and existing structures and IBM's perspective. It's being presented by two speakers. The first speaker is Marius Loeffler. Marius Loeffler is Innovation Manager at DIN, which is the German Institute for Standardization. And the second speaker is Oliver Oberst. And Oliver Oberst is working at IBM and is responsible for quantum sales and quantum technical. It's also a quantum technical ambassador for IBM. So we are very interested in your views when it comes to standardization within quantum computing and quantum technologies.
Yeah, thank you very much for this great introduction. And I guess I start my talk. Can you see my screen now?
Yeah, perfect. We can see it.
Oh, great. So, as you already mentioned, my name is Marius Loeffler, and I'm coming from DIN. DIN is the German Standardization Institute. And I start this presentation with a very, very brief introduction on how standards in quantum computing are developed, what standards are about, and what standardization activities already exist. And after me, Oliver Oberst will give the perspective from IBM on the development of standards for quantum computing. But if we go deeper in the world of standards, we have to, one second. We have to summarize what is a standard exactly. And in a few words, a standard is an agreement on how to do something in order to be able to repeat it with the same result. And those agreements are developed by the experts of a consortium that has agreed on relevant requirements. And those requirements are, for example, the determination of characteristics, features, criteria, or attributes of products, services, processes, or systems. So that's a very, very short introduction on what is the standard about. And the most important thing here is the question, where are those experts? Who are those experts? Where are they come from? And the simple answer is you are those experts. You are developing standards in relevant fields like quantum computing, quantum sensing, whatever. And if you're able, or if you want to participate in those standardization activities, you might contact your national standardization body. Standardization is based off some principles. At first, standards are voluntary. That means it's voluntary to participate in standards, and it's also voluntary to use standards. Standards are always public so that everybody can read them. And standards should involve all interested parties or stakeholders, for example, the industry, the research, governments, policy, consumer protection, whatever. Standards are always consensus-based, and standards should always reflect the current state of the art. And it's very important that we have a big bunch of standards who are coherent, though that you don't have two standards on the same topic. And the sentence at the bottom is also very, very important, that unlike laws, standards are not legally binding, and their use only becomes binding when this is stipulated in a legislation or in a contract. So we have several standardization activities in the whole field of quantum technologies. And for this talk, I focus only on the standardization activities that are relevant for quantum computing. And those are these standardization institutes like DIN, where I come from, like ISO, the International Standardization Organization, ISC, which is also international standardization for electrotechnical stuff, and SEN and SUNLAG as European counterparts of ISO and ISC. And for example, we have some first documents ready at DIN at the national level, for example, the DIN spec 91444 with a title definition of a quantum computer resistant encryption scheme, which specifies an algorithm for secure your data today against quantum computing attacks for tomorrow. And we have also an standardization idea at the moment for the benchmarking of quantum computers. And if you're interested here, you can contact me afterwards and maybe we can work together on this item. Then we have at the international ISO IEC level, the working group 14, quantum computing, which is led by China. And they have actual 2 work items in their work program. For example, the first one on the standard on the terminology and vocabulary, and a very new standard without a number, which specifies or which describes an introduction to quantum computing. And at the European level, we have the Sen-Sonderlake focus group on quantum technologies, the FGQT, which is led by Germany. That group was founded in the middle of 2020, has over 160 experts, around about 20 or 23 meetings, and around about 200 contributions. And the main goal of this group is the coordination between ISO, IEC, ETSI, ITU, QUIC, the Quantum Flagship, and other organizations. And the main goal of this focus group is the elaboration of a standardization roadmap, which describes what needs to be standardized and when does this to be standardized, and which standardization organization should standardize those topics. And we hope that we can publish a first version of the standardization roadmap in the end of summer of this year. And I guess that's already my start or everything I want to share here. And if you are interested in participating in the standardization of quantum technologies, feel free to contact me and we can elaborate different ways, different methods. And now I would like to hand the stage over to Oliver Oberst from IBM so that he can share his perspective on the world of quantum standards.
Okay. Thanks, Marius. Thanks, you got the unshare, yes, and let me bring up my slides. So now we'll have a look at the IBM perspective of what might be interesting aspects in standardization or normalization processes. I cannot give you like the holy grail of how it should be. That's not the point of this talk. I can give you aspects which we think might be relevant and also some experience we see. So quantum computing is actually not that an island of several few people who can work with, because since we opened up in 2016 our IBM quantum systems, only in the IBM systems we have already over 400,000 registered users, which have run 1.5 trillion of actual quantum circuits and over 4 billion of hardware quantum circuits on a typical day are executed. We have around about 24 systems. That depends on how many are just commissioned. So some go out and some new one will replace them. So at the moment there are actually 22, but usually we are in the order of 24 systems which are online for usage outside of IBM, so for the general public. And then there are free systems freely available for everyone, like you don't have to actually pay for it. You just log in with a Twitter account, a GitHub account, an IBM account if you have one, or a Google account, and then you can just run on those systems. And one of the main aspects why we did that is, you see on the bottom, we have now over 1,400 papers, scientific and research papers, which are published, which more or less leverage those IBM quantum systems. And so that's one of the goals why we opened up, and this is the key point here, open access to the technology to actually accelerate the research on the algorithm mainly and software side. Whereas we as IBM see us as we are following a path and a roadmap to develop the platform, the quantum computing platform itself. But As we have seen in the past with traditional computing, in the beginning on the ENIAC system, you had a handful of people who were able to access those systems 70 years ago. And that's why it also took decades that the actual application and use cases were implemented on those systems, because only a few people, only a few brains were working on the programming side. And that's why we opened that up. And obviously we can show that this has the effect we wanted to have here, so that we can accelerate the scientific progress in the area of quantum computing. The systems are easily accessible and very transparent, so you can see all the details online, and you can see how many qubits, what is the error rate, what is the so-called quantum volume, what the disk we will see later, and so on and so forth. Very transparent. And then also we have, since 2017, the IBM Quantum Network. So this is not freely available for everyone. So you actually have to apply for membership in the IBM Quantum Network. And the goal here was for those who seriously want to do research on quantum computers on the application side, on the use case side, we wanted to streamline their efforts and put them together in a network, so that there is collaboration with IBM and with each other in the network. In terms of German participations, we have, for example, Daimler, E.ON, Fraunhofer, University of the Bundeswehr, DESI, very new in the quantum network, SVA, ZF, we have University of Stuttgart, University of Saarbrücken. And in total, we have now 183 members in the IBM Quantum Network. And to look a little bit more into the detail, from the German point of view, we have now 10 members. The United States is clearly leading, followed by Japan and Canada, and then Germany is on the fourth place in terms of members in our IBM Quantum Network. Why do I'm talking about who is all in the IBM Quantum Network? Because it's very important to see there is a lot of interest, and there is a lot of necessity for close collaboration. So we have a lot of stories where IBM research published an algorithm, then a university took that algorithm and improved the algorithm, then an industry partner from the quantum network took actually that algorithm, which was twice improved, the publication from it, and then they applied it for their use case. In this case, for example, JP Morgan Chase applied such a case for option pricing, and then they published it again, open source the code in our open source software framework, Qiskit. And so everyone can now actually do the tutorial how to do option pricing with quantum computers. This is the an example how the IBM Quantum Network works. And for sure, we have a lot of academic research members in government and research centers, but we also have quite some industry members, for example, from aerospace and defense, from automotive, a very, very strong participation on banking and financial services, as well as electronics and technology, for example. Then we have some special partners, like, for example, Fraunhofer or the University of Tokyo, where we actually have dedicated systems. So for Fraunhofer, we built a system in Ehningen near Stuttgart. So this is exclusively in access by Fraunhofer and their partners, which they bring into the IBM Quantum Network, and doing joint research together with Fraunhofer. So collaboration, very important, but now let's look more at the facts and figures. So what are the actual metrics IBM sees which are important to define or to describe the power of a quantum computer? And we saw earlier in Marius' talk that there is an idea to have something for a standard or norm for the benchmarking of a quantum computer, and this goes into that direction. So pretty early on, it was clear that there are several dimensions you have to look at. In the beginning, everyone was just talking about the number of qubits. Yeah, that's the scale, but that's not sufficient because we have today we have the NISQ system, near intermediate scale quantum devices, which have an error rate on each operation and so on and so forth, which have limitations, and this has to be somehow measured. And that's why a couple of years ago we introduced the so-called quantum volume. And this is a measure of the actual quality of the quantum computer. And then last but not least, pretty new since the end of last year, we defined a new KPI, which is called CLOPS, circuit layer operations per second, which gives a metric for speed of the quantum computer, which is also very important. By looking at the scale, as I said, in the beginning, everyone was just like 10 years ago, everyone was talking like how many qubits could you do? But I mean, you could do thousands of qubits, but if the error rate is very, very, very high, and if you cannot couple, entangle many qubits with each other, then, well, it's not it's of no use talking about just the number of qubits. It's very important, but because it shows you what kind of algorithms you can run, what kind of circuits, because very complex circuits need many qubits. But it's not the only KPI you can use here. However, it's one of the most important to progress if we want to see quantum advantage soon. So what we see here is a depiction of our Eagle chip we released end of last year, and it's in use now from IBM Quantum Network members, and it has 127 qubits. And it was the first chip we built with 3D stacking methods to just fit all the qubits on the die of the chip. And there you see, for example, one of the limitations: we cannot build indefinitely large chips with many thousands of qubits. But we see that later. On the quality side, we have the quantum volume. On the quantum volume, it's published. There is benchmark code available externally, so you can actually run the benchmark on your own quantum computers, and the industry adopts it. So there are many other vendors of quantum computing technology which have published quantum volume figures for their systems. IBM has a very good pathway which shows that we constantly improve the quantum volume, and it's published and everyone can actually use it. On the speed side, we have the CLOPS, the circuit layer operations, and here we actually wanted to introduce also a measurement of speed, because different types of quantum computers, quantum bits, they have, specifically on the speed side, they have very, very different characteristics. And also this is published, and you can actually see how the measurement should be done, and actually do the measurement by yourself. But this is, as you see, these are no norms or standards. So these are published things from IBM. So it might be really helpful to have something really well defined where everyone actually knows how to do it and knows how to do it in the same way, so that it's actually comparable. We had in the past the case that quantum volume was published, but the measurement was done in a slightly different way. So is it then again comparable to the quantum volume one company publishes or the other? So here norms and standards might be really helpful. Another thing we saw over the yesterday specifically also, and so also today, is it's also important not only to look at the individual quantum computer and the quantum chip, what are the metrics for it. It's also very important that the applications typically run hybrid, so classic and quantum hand in hand. We saw the talk from the keynote from IQM yesterday, where this was a very, very strong topic to bring HPC and quantum together. And so in the end, what counts for the researcher is the runtime of the full application, meaning the classical part plus the quantum part, and so on and so forth. So this is also a thing which you have to keep in mind. And it's a very hot topic to bring this thing together. IBM has the Qiskit runtime to bring classical and quantum close together. And then also we have the open Chasm, which is a quantum assembler language standard, basically an open source standard, where we are working closely to improve that every time. And by using the Qiskit runtime and by actually using the latest system, for example, we could improve this analysis we had published 2017 in Nature by a factor of 120 times in terms of improvement of this chemistry simulation. Open Chasm, I already explained. This is very machine close, so very close to the actual quantum computer. And here it's very important to have some kind of a format in between and an interface, how actually you can exchange code from one framework to the other, from one system to the other. So openness also on that side, on the software side, open source, like we do it with Qiskit and with Open Chasm, is very important in our view. And then last but not least, we saw 2 days ago, actually, an update of our roadmap. Here in green, you see what we actually reached in time. And now we are really changed the gear. So the old roadmap was depicting up to Condor. And now we actually have a roadmap, and you are invited to read the research blog. It's publicly available since two days, how we will reach over 4,000 qubits by 2025. Don't miss it. It's really interesting, and the technologies are at least somehow depicted how we will reach that by 2025. And as said, we have more than 1,400 papers published based on IBM Quantum. And this is why it's very important to have open interfaces, open access. And the metrics are pretty important, because now that there are so many vendors, you have to have, as a user and as a procuring entity, at some point you have to have something in hand to actually compare the systems with each other. And that was the last point of my talk. Thanks.
Thanks a lot for the presentation. I have two questions, one addressed to both of you. So the question to Marius Loeffler from Dean is, how do you think one can incentivize companies like IBM or other companies relevant in the quantum computing and quantum technology field to invest more resources into standardization? What is the concrete USP and benefit for them? And the second question, directly as a follow-up to Oliver Oberst from IBM, is could you explain us a little bit how does IBM engage in standardization on all levels and layers, like national standardization in Germany, European standardization organizations, and international organizations?
Okay, may I start?
Yeah.
Okay, I don't know whether I get your question right. I would say the main point of participating in standardization is that you can decide today what the standards from tomorrow are, and this is the most important thing, that you can describe what the market needs in a few years, and therefore it's I guess it's the simplest answer.
Okay, thank you.
Yeah, and the question which went in my direction. So we are a global company, and so we have technical experts usually in the different areas which are engaged in those local standardization efforts. Like here in Germany, we have people who are part of some of the DIN work groups, and then in other areas we have other technical experts who are engaged there, and there is a synchronization internally between them.
Thank you. So I think the conclusion of this speech is really to look onto the technologies evolving and really to watch out what's happening in the standardization landscape and to engage. Thanks a lot for the presentation and the very interesting insights. So after this presentation, it's 12:35 now, or 12:40 already. So we have a 20 minutes break now until 1 p.m. At 1 p.m. we go on with a program on this stage Bob, and also on the stage Alice, with an afternoon program of the Quantum Summit of Bitkom. So have a nice lunch break and see you soon back on the stages with the interesting program of the Quantum Summit 2022. See you soon at 1 p.m.